Welcome to our first live video recording. This is the first time you students will see me in person, I think. I'm going to try and do these recordings this way to make it be a little bit faster. Okay, so on this chapter, this part of the chapter which we are finishing up, chapter 16, we're going to be talking about a couple of the final topics. One of them, which we're going to talk about now, is what's called radiation heating and global warming. Now, radiation heating is the third of the three topics of heat transfer. We've talked about conduction and we've talked about convection. Now we're going to talk about radiation heating. First, we'll start off with an example. The most obvious is solar heating. Obviously, even on a cold day, an object in a car, for example, can warm up considerably just from the radiation from the sun. It's a transfer of energy or light waves from the sun, and it propagates through empty space. The radiation heating does not occur until the radiation reaches an object. The energy of the radiation is absorbed, and it adds the heat to the object that it's in touch with, and then we see the temperature rising. So in these three examples, there are three examples of different types of radiation: radio waves, infrared waves, and light waves. We'll talk a little bit more about them as the slides progress. Radiation energy, as the slide says, is transferred energy that is another modality, not exactly like conduction and convection, but in addition to conduction and convection. It does not require a physical contact between substances to transfer the energy. The solar heat from the sun, the solar radiation, propagates through empty space and it heats the earth. So we don't have to have physical contact, unlike conduction heating and unlike convection heating. Then we get some general properties about objects. All objects at any given temperature will radiate energy in the form of electromagnetic waves. This was discovered at the end of the 19th century, and a particular form of it became known as blackbody radiation. The basic idea is that even though we cannot see the rays emanating from our bodies or from objects, they nevertheless produce radiation, usually in the form of infrared. So infrared rays or radiation is the radiation from the thermal or the temperature property of a material. All objects, so that will have this property. And this radiant energy is in the form of electromagnetic waves. We'll try to give you an example of that because we haven't got to that section yet. But basically, if you think of a water wave, for example, that we're very familiar with, the electromagnetic wave is an electric and magnetic force that propagates through space as a wave. If the temperature of the object is higher than its surroundings, then it will emit more radiation than it absorbs. And conversely, if the radiation energy falls on a cooler object, then the object will heat up, and this is called radiation heating. So if the temperature is higher than its surroundings, it will emit more radiation. If it's cooler than its surrounding, it will absorb more radiation. So these are some general properties, and we'll talk more about it as we go on. Properties of electromagnetic waves. They are like water waves in the sense that they travel away from the source. If you drop a pebble on a surface of a pond, the waves propagate away. If we turn on a light bulb, which you can see the three examples from the previous slide here, then the light waves propagate away from their source. If I have a radio station transmitter, then it will also propagate waves away from the source. Now, these waves are not visible to us, to the naked eye, but we now know that these are forms of waves that act like the oscillating electric force and a magnetic force. And we call them electromagnetic waves, which is in the title of this slide. So, emission of radiant energy. Every object above absolute zero temperature will radiate some form of electromagnetic radiation. As we said, normally it's in the infrared, so we're not going to be able to see it visually. But if we heat an object up, such as an electric burner on the stove, it eventually becomes red. The red hot is the redness, is the color, because the wavelengths are getting short enough that we can actually see them with our eyes. But every object will radiate at any temperature above absolute zero. From the sun's surface comes, of course, a visible light in the form of electromagnetic waves or radiation, and we call this solar radiation. But these are oscillating electric forces, we call them electric and magnetic fields, and they will arrive on the Earth or at an object's surface, and then that will induce the heating when they are in contact. From the Earth's surface, there's also a form of radiation that comes from within the Earth. The core of the Earth is very warm. It keeps the ground cover, the ground, and the upper surface levels of the ground warm. But at any rate, whatever the temperature is on the surface, it will have some radiation. And we call that terrestrial radiation. Again, we don't see that like solar rays because the wavelengths are too long for our eye to actually detect it. But the Earth is radiating energy all the time. It's also receiving energy and being heated up from the sun. The sun is much hotter than the Earth, so Earth is a net absorber of the sun's, I call this EM, which is short for electromagnetic waves, which helps keep it warm. So example of a wave. We can also make a wave by shaking a rope that's attached to the wall. You see the girl here shaking it, and you are giving a demonstration of what is the difference between a low frequency wave with a very long wavelength or a very high frequency wave, which means that she's shaking up and down much more rapidly, and the frequency of her pulling up and down on the rope increases, so the ripples on the rope are closer together. Just as you see here with the rope, so light is also made up of waves, and it can have short wavelengths or long wavelengths. It is related to the frequency of vibration. The lower the frequency, the longer the wavelength, and vice versa. Radiation or a light wave is a traveling wave of electric and magnetic fields. So this is just some background so that you have some intuitive feel before we get to that section. Now, another property, as we talked about earlier, is that as you heat an object up, it creates this the radiant energy or electromagnetic waves at different frequencies. And the general property is that the higher the temperature of an object, the higher the frequency or the peak frequency will be. So as you heat up an object, its frequency that it emits electromagnetic radiation also goes up. And at some point, if you heat it up high enough, you will get some light that is in the visible range and we'll begin to see it, such as the redness of a hot stove. So there's a range of temperatures of radiating objects. Room temperature emission is in the infrared, as we've talked about. That's not visible. Once the temperature gets up above about 500 degrees Celsius, then we begin to see the red light emitting, which is the type you see coming from a hot electric stove. And then if you go even higher, eventually when you get up to 1500 degrees C, then the object will emit you'll see all colors being produced, and when that happens, they add up to white. Example of that is a heated tungsten light bulb. So the old-fashioned incandescent bulbs produce their light by heating up a material. Now we can translate this into global warming. And the reason why it's often called the greenhouse effect is because there's a similar effect in a florist greenhouse that causes the heating. Many of you will have noted that if you go into a greenhouse, it's generally much warmer than the outside air temperature. So this is an effect that has been known or observed for some time, but the explanation is a little more involved, and it needs to involve some of the principles that we just talked about. The basic idea is, let's talk about the actual greenhouse itself first. It's a glass structure around the plants and flowers and vegetables that are placed inside. The effect is that, or what happens is that there is short wavelength radiation from the sun that gets transmitted through the glass. And when it does, it will get absorbed on the flower, the plant, or the ground. At that point, what happens is that these objects, because they already have some temperature and because they're getting warmer from the incident sunlight, radiate their own infrared energy. Remember, all objects radiate regardless of temperature. So even if we are at room temperature, objects will still radiate in what we call the infrared spectrum of wavelengths. So they give them back off. But now what happens is not transparent. to that radiation. In other words, it absorbs it and it re-emits it and it comes back again. So instead of letting that heat escape, it's like a one-way valve that is only letting short wavelength radiation in, but blocking the longer radiation when it tries to get back out. Now that is not shown on this graph, but in fact, the longer wavelength radiation that's re-emitted from the objects in the greenhouse gets effectively reflected back, and then it gets reabsorbed into the plants and to the air, and then it makes it hotter, and then they reabsorb, then they emit infrared radiation again, and that radiation gets blocked and reflected back. So they're constantly getting their own radiation back to them, which is not allowing it to escape. It's like wearing a very warm parka in the wintertime and there's no outlet for the heat. So the objects inside continue to increase in their temperature. So this is the actual greenhouse effect, and we'll show exactly how that works when we talk about the atmosphere. Understanding the greenhouse effect requires two concepts. Keep in mind, all things radiate, not just hot things, but cold things as well. Not only does the sun radiate, the earth also radiates as well because it has a temperature. Therefore, there will be this effect going on regardless of its temperature. Now, the transparency of light through the atmosphere depends on the wavelength of radiation, which is what we showed in the last slide. The glass allows the short wavelength light to come in, but the re-radiated light or radiation from the ground and the pots get trapped and cannot escape. And that's what's called the greenhouse effect. And we see this happening in our own atmosphere, which is in the news quite frequently now. So for the greenhouse effect, two types of radiation events occur. Suppose we consider a car's heating by the sun. We would say that in this case we would be able to observe excessive warming of the car's interior. And this occurs when the windows are closed on a hot sunny day. It also gets significantly warmer on a cold day, even if it's out and it is and the sun is shining very, very brightly. The two types of events that are going on here is sun's rays are very short wavelength and pass through the car's windows. The absorption of the sun's light waves by the seats and interior warms the car. So the light from the sun does get absorbed. It comes through the windshield, gets absorbed onto the interior, the car warms up. Now the car radiates its own waves, which are longer and don't transmit through the windows. Consequently, that radiation gets trapped, it reflects off of the windows, and it gets reabsorbed by the car's interior, thus causing the car's interior to get warmer. And in some cases will be very hot on a warm day. And it can be as much as 20 or 30 degrees warmer than the outside air temperature. How does this actually work in our Earth's atmosphere? Well, much of the visible and ultraviolet sunlight is transmitted through the atmosphere. Some of it does get absorbed or reflected, but a great deal of it, and here you see the solar light rays coming in to the Earth, and they make it through much of it makes it through the Earth's atmosphere. What you see here in the black dots are the particles of different molecules in the Earth's atmosphere that can cause absorption or re-emission of the light at a longer wavelength. If it gets absorbed by the Earth, which it certainly will when it reaches there, this will cause both ground and air heating, and therefore the Earth re-radiates longer wavelengths as terrestrial waves that is generated from the temperature of the Earth and is trying to effectively breathe and not get overheated. So that radiation from the Earth tries to escape, which you see as longer wavelengths coming out here. And much of it, or a lot of it, does. But increasingly what we find happening in our atmosphere today is that these longer wavelengths that are coming out from the Earth, which is at some temperature that we find at various points around the globe, cause the infrared radiation to come out. But this infrared radiation going out is trapped. It cannot continue out into space. It gets absorbed and re-emitted, and this longer wavelength would come right back to Earth, and the cycle of reabsorbing its own energy gets added to the constant input of the solar radiation, and consequently the Earth's atmosphere begins to heat up. Now this is a natural process, and it's expected this happens to some degree, but the more detrimental effects happen when we add things like CO2 into the atmosphere. So adding carbon dioxide will cause more absorption of this terrestrial radiation, re-emitted back to the Earth, gets absorbed again on the Earth heats up, and we now have more trapping of that terrestrial radiation. This is a cause of concern because adding CO2 is causing more of that terrestrial radiation to come back to Earth, and instead of allowing it to breathe and cool off. Continuing on this explanation, so we saw in the last slide about what is happening as the rays come in and cause the Earth to heat up. The terrestrial radiation gets absorbed by the atmospheric gases and then re-emitted back to Earth. So this is the trapping of that radiation coming from the Earth. It doesn't get to escape, it gets re-radiated back to Earth. We could call it reflection. So since it's unable to escape and it's coming back to Earth, it causes the Earth to warm up when that reflected radiation comes back to the surface. Now, more terrestrial radiation is emitted by Earth when this happens, and it again gets reflected back to Earth, and so it's a cycle that keeps continuing, and this cycle then causes the Earth to heat up, because every time it tries to re-emit or emit its terrestrial radiation, it gets bounced back, and that bouncing back causes it to heat up. Now, some of this is a natural phenomenon, but as I mentioned earlier, that there are certain molecules in the atmosphere that reflect these long wavelength terrestrial radiation and cause them to come back to the Earth. And particularly the molecules that are responsible for this radiation trapping, what we call methane gas, nitrous oxide, and carbon dioxide. So we've heard a lot about carbon dioxide in the news and the need to reduce that. This will help reduce the greenhouse effect so that more of the terrestrial radiation can escape. As we know, molecules such as these have large man-made contributions from our cars and electrical energy consumption, and has led to the problem that we now face, which is called global warming. So that in a nutshell, that's the description, and that is the reason we call it the greenhouse effect. So check your understanding. Here's a question for you. The greenhouse gases we've mentioned greatly contribute to global warming by absorbing more visible radiation than infrared, more infrared radiation than visible. Visible radiation and infrared radiation contribute about equally, or D, to very little radiation of any kind. Well, obviously, I think most of you would agree C and D are probably not the ones that we wanted to look at. And based on what we've been talking about, the greenhouse gases greatly contribute by absorbing more infrared radiation than visible. Now, one thing to keep in mind is that while the energy of the sun is keeping us alive and well, it's also causing the Earth to overheat, and we know that we are going to have significant rising of the coastal waters due to this rising ocean and the melting away of the polar caps. One way that is moving in the direction to alleviate this is to build solar panels. And solar panels is really the wave of the future and the present. Places like California are already using sources of renewable energy for 20% of their electricity, much of it these type of solar panels. But solar panels also work well now in northern climates as well. You don't have to have direct sunlight, even though it's less efficient. You still can have electrical energy source in northern climates using these panels. And these panels are converting the radiation of the sun directly to electricity. One quote here from scientists from Caltech: more light energy from the sun hits the Earth in 1 hour than all of the energy consumed by humans the entire year. If we don't tap into that source, we clearly are not going to make a significant dent in reducing the carbon emissions and therefore reducing the impact of global warming. So this is all moving us in a good direction. Finally, what we have here on this one, before we wrap up, by the way, I will also mention on this lecture that there are 6 or 7 or 8 slides that I will post on Blackboard that will have additional questions for you to look at and answer and review. You can open up that PowerPoint the next time you are you're on Blackboard. The final and last topic we're going to talk about is Newton's law of cooling. So Newton's law of cooling says that the rate at which an object will heat up or cool down, but we can look at either way, is proportional to the temperature of the object minus the temperature of the surrounding. Let's say, for example, you put a hot apple pie in the freezer. Obviously, it is going to reach room temperature much more quickly than if we leave it on the kitchen table. Newton was the first one to observe this, that the rate at which the temperature changes is proportional to the difference between the object's temperature and the temperature of the surrounding medium, or air, if air is the medium. That's an important consideration. A warmer house leaks more internal energy to the outside than a house that is less warm. So again, the temperature difference determines how rapidly that heat is escaping and how rapidly a temperature change can occur. Newton's law of cooling applies to the rate of warming. Objects cooler than its surroundings warm up at a rate proportional to the temperature difference, called delta T. This is the temperature of the object minus the temperature of the surroundings. And the greater this difference, the greater will be the rate of cooling or the rate of heating. Similarly, frozen food will warm faster in a warm room or in an oven set at 300 degrees than in a cold room. We all have this as a very common experience, but Newton was the first one to discover it. It is commonly thought that a can of beverage, so this is a last final test question, a can of beverage will cool faster in the coldest part of the refrigerator. Knowledge of Newton's law of cooling will support this knowledge. Will show this knowledge is incorrect. It may or may not support this knowledge. It depends on other factors, or it may or may not contradict this factor, which may depend on other factors. So the correct answer is A. It supports this knowledge. When placed in the coldest part of the fridge, the delta T will be the largest, so it will cool the fastest. So that's our final point. This is the end of chapter 16. It's the end of the chapter on thermodynamics. So next time we will start the section of the chapter